Hello everyone, my name is Brent Beck, and today I'm going to be talking about direct use geothermal. This topic is covered in Chapter 12 of William Glassley's Direct Use of Geothermal Resources. The following clip will give some background on direct use geothermal energy. It will introduce both the applications and the motivation behind the technology.
Where in Indonesia, geothermal heat is increasingly being used for other applications as well, such as drying tea leaves for processing. In the USA, geothermal energy has many agricultural applications. Vegetables, flowers, ornamentals, and tree seedlings are raised in 43 greenhouse operations heated by geothermal energy. 49 geothermal aquaculture operations raise catfish, tilapia, shrimp, alligators, tropical fish, and other aquatic species.
We formed the company 2 years ago. Basically what we did, we converted existing chicken houses into fish houses, and we hope to be completed with this project by August of this year. A fantastic species in a hybrid striped bass. They take 11 to 12 months to grow out to 1.5 pounds, and this farm can produce 300,000 to 400,000 pounds annually with hybrid striped bass, and flounder take about 16 to 18 months to grow out. And with that business plan, we should be able to put out 80 to 100,000 pounds of flounder. We put towards geothermal heating and cooling. They are 90,000 BTU units each, and they only use 11 amps each as well. We also received a grant, a $45,000 geothermal grant from Rural Development.
Agri-industrial applications include food dehydration, grain drying, and mushroom culture. The drying of onions and garlic is the largest industrial use of geothermal energy.
Here we have listed some of the main applications for direct use geothermal. As you can see, the list is broken down into 4 main categories: materials manufacturing, drying, production of food products, and miscellaneous. Also shown are the temperature ranges associated with each product. It is clear that none of these processes require temperatures as high as required for electricity generation. This is the key reason why direct use geothermal is suitable to more places than geothermal power plants. This graph shows the amount of energy that direct use has supplied over the years. The graph is broken down into 6 categories, similar to the previous graph: geothermal heat pumps, bathing and swimming, space heating, greenhouse heating for year-long production of seasonal or exotic crops, aquaculture pond heating, which is essentially heating large ponds to allow non-domestic species to survive in different climates, and they will also grow faster and larger in these hotter temperatures, and various industrial uses. Regardless of which application you look at, it is clear to see direct geothermal is on the rise, nearly doubling in a 5-year interval for some applications. This can be attributed to more implementation of these direct use systems, as well as their improvements in technology. These direct use systems rely on efficient heat transfer from inside the earth. This is usually accomplished through the use of a conductive fluid, such as water or air, that is pumped into the earth cold and returned heated. Glassley's direct use of geothermal resources lists 4 main modes of heat transfer. In addition to the commonly known methods of conduction, convection, and radiation, evaporation is also listed. It will be seen that while not well known, evaporation can be a dominant mode of heat transfer in these systems. A representative quantity of heat transfer is the heat flux. It is measured in units of watts per meter squared or joules per second per meter squared. In order to calculate the total amount of heat transferred, this flux is multiplied by the involved area. It will be seen that these modes do not occur separately, and instead all play a part in the direct use systems and must be accounted for. It goes without saying that these modes of heat transfer and the mechanisms behind them can be very complex. To give an in-depth explanation is a pretty tall task to accomplish in such a short amount of time. So without getting too technical, the goal of this presentation is simply to introduce each mode and provide enough background to be able to understand how their fluxes are calculated. The first mode of heat transfer we will look at is conduction. Conduction is the quantification of vibrational energy being transferred between atoms. A common example of conduction is the heat being transferred through a frying pan on a hot burner. The flux for conduction is calculated through the relation shown here. In this equation, K is the thermal conductivity in watts per meter per Kelvin. This is a property specific to the material conducting the heat. The table shown to the right gives some sample values of these thermal conductivities. As expected, metals are the most conductive materials listed. Going from the top of the list to the bottom, there is a trend in conductivity based on the phase of the conducting matter. Solids tend to be the most conductive, followed by liquids, and lastly gases. This can be imagined when considering the amount of space between molecules in each phase. The farther spread apart they are, the less easily they can transfer vibrational energy to neighboring molecules and atoms. The other value that dictates the heat flux in conduction is dT by dx, or the thermal gradient. This has units of Kelvin per meter. It is the temperature difference on either side of the conductive material divided by the thickness of the material. The next mode of heat transfer we will examine is convection. This is the transfer of heat from a surface to its surroundings. A common household example is the heating element in an oven heating the air inside, hence the name convection oven. The heat flux for convection is calculated similarly to that of conduction. This general form for the heat flux is pretty consistent throughout all of the heat transfer modes. Typically, there is some sort of gradient and a constant depending on the conditions. In convection, we have the relation shown here where we are multiplying the convective heat transfer coefficient H by the difference in temperatures between the hot surface and colder surroundings. The value of H with units of watts per meter squared per Kelvin is a fairly complex constant. It is dependent on the fluid in which the convection is occurring, the flow of this fluid, geometry of this scenario, and more. It is usually determined experimentally in most real-world applications. This is typical when looking at the overall heat transfer in a system as well. Sometimes a single coefficient and relation can quantify an entire system's heat transfer. Simplistically and conveniently, however, Glassley's book lists the value for this coefficient for airflow as 9.045 times v, with v being the velocity at which the air is moving. Some more of these coefficients are listed in the table in the next slide for reference. The temperatures T surface and T surroundings can be measured in either Celsius or Kelvin, as their difference will be the same regardless. Listed here are some of the other convective heat transfer coefficients that Glassley's book lists. Each scenario is clearly unique and specific, further illustrating the need for experimental values in technical applications. These values can be very useful, however, when solving simplified models or approximating a similar system. Now we will examine heat transfer by way of radiation. Radiation can be thought of as the heat being given off from a hot surface in the form of waves. In this mode of heat transfer, our representative coefficient is emissivity, expressed by epsilon in the equation below. This value is unitless and usually a function of the temperature of the surface emitting the radiation. The value can range from 0 to 1, with 1 corresponding to a perfect emitter or a black body. There is sometimes an added parameter relating to the geometry of the emitting surface. This value, however, is rather complex. We can utilize the flat surface assumption with a value of 1 for our purposes to simplify the calculation. The radiative heat flux also utilizes sigma, the Boltzmann coefficient, with a value of 5.669 times 10 to the negative 8th watts per meter squared per Kelvin to the 4th. This mode of heat transfer is one of the more complex modes of heat transfer we will deal with, but by making some strategic assumptions to simplify it, we can still effectively calculate its flux in basic models. The last mode of heat transfer we will look at is heat transfer through evaporation. This mode is most similar to convection in its mechanism, and this is reflected in its formula. Looking at the equation, you can notice that there are more than just one constant in this equation. Both A and B relate to the velocity of the fluid at the liquid surface. You can see that as this velocity increases, so will the values of A and B, thus increasing the flux, just as a faster moving fluid would increase the flux in convective heat transfer. PW and PA correspond to the water vapor saturation pressures at the temperature of both fluids. These values serve as the representative gradient in evaporation and should be in units of kPa. They can be found by a simple Google search, or there are even apps that give you the respective value at the desired temperature and conditions. The last value in this equation is the evaporation constant. For our purposes, in water to air heat transfer, this value can be assumed to be 1. Now that we have covered the 4 basic modes of heat transfer, we can examine a system and attempt to quantify the heat transfer occurring inside it. When considering the main goal of a direct use system, it's pretty obvious that they are made possible by the heat transfer from the earth to the working fluid. The heat transfer does not stop here though. Throughout the entire system, some of this heat will actually continue to dissipate, thus unfortunately hindering the system. Any heat transfer after the peak temperature is reached that is not a direct and intentional application is actually undesirable and is considered heat loss. When looking at a system, the heat loss can be quantified as the sum of all the modes of heat transfer. This is a key calculation in determining the amount of energy required to run the system. Heat loss can dictate both the size of the direct use system needed and can even sometimes determine whether or not direct use geothermal is practical in the given situation. Here we have a diagram of a large direct use system. Each individual component in the system will have a set amount of heat loss associated with it, and also a set amount of heat that is needed to effectively run and accomplish its goal. In the next few slides, we will examine just a small part of a similar system to take a quantitative look at the heat loss occurring. In this sample problem, adapted from Glassley's book, we will look exclusively at the heat loss in a basic aquaculture pond to keep it simple. The pond described in this problem is cubical with dimensions of 10 meters long by 10 meters wide by 10 meters deep. It has 1/4 meter or 25 centimeter thick concrete walls. The pond's water temperature can be assumed to be kept constant at 25 degrees Celsius. The temperature of the ground surrounding the pond and the ground surrounding the pond's walls can be assumed to be a constant 10 degrees Celsius at the practical depths defined in the problem statement. The air is defined to be an average of 20 degrees Celsius as well. In this scenario, the pond can be assumed to be a black body and there is a 2 meter per second breeze over the pond surface. To start this problem, we want to begin by looking at each mode of heat transfer separately and finding their individual fluxes and eventually their corresponding heat losses. First, we will take a look at the role conduction plays in the system. Due to the temperature difference between the pond water and the ground temperature surrounding the walls, there will be conductive losses through the walls and base of the pond. We can begin this analysis with the basic equation for conductive flux. Since we know the walls are made of concrete, we can simply take the value of the conductivity directly from the table shown to the side as 1.4 watts per meter per Kelvin. Now we need to determine the thermal gradient. This is just going to be the pond temperature minus the ground temperature divided by the thickness of the pond walls and base. Plugging everything in, we are able to solve for the flux of 84 watts per meter squared. With this flux, we only need to multiply by the surface area to get the total heat loss from conduction. Since we have a cubical pond, all sides are 100 meters squared, and since there is no conduction occurring through the top, we only need to account for the 4 sides and the bottom. Multiplying will give us our conductive value of 42,000 watts or joules per second. Now let's take a look at the heat loss from convection. We can start once again with the basic formula for convective heat flux. First, we need to find the convective heat transfer coefficient. There is no need to use the table if we remember that this value can be approximated by the relationship 9.045 times V, since we are looking at airflow over a surface. Plugging the 2 meter per second velocity of the breeze blowing over the pond will give us the value of the heat transfer coefficient. Now we only need to plug in the values of the air temperature for the surroundings and the pond's water temperature for the surface value. Since this is a difference being taken, we are able to keep the temperature in the provided units of Celsius. This allows us to be able to solve for the flux of 90.45 watts per meter squared. Once again, applying this flux over the relevant area, which in this case is just the exposed top surface of the pond, or 100 meters squared, gives us the overall heat loss through surface convection as 9,045 watts or joules per second. Now we will examine the effect that radiation has on the system's heat transfer. We can start the same way as the previous calculations with our basic flux equation. We can immediately fill this in with our common knowledge of the Stefan-Boltzmann coefficient. The temperature of the surface and surroundings will be the same as in the last question, but now we need them in units of Kelvin to make sure the units match with the Stefan-Boltzmann coefficient, and we get a flux value in watts per meter squared. This is done by simply adding the Celsius temperature to 273.15. The last piece of information we need to fill in this is the emissivity. In the problem statement, it was said that the pond was a black body. This corresponds to an emissivity value of 1, as stated previously. Now we can solve for the flux of 29.30 watts per meter squared. Multiplying by the surface area of the top of the pond, we get the final value of the radiative heat transfer as 2,930 watts or joules per second. The last piece of information we need to solve this problem is the heat loss from evaporation. We can start one last time with our original flux formula for evaporation in this case. To fill in the values of A and B, we need their formulas. Simply plugging in the velocity of the breeze from the problem statement into the equations for A and B gives us these values. We now need to find the values of the water vapor saturation pressure at both the temperature of the water and the temperature of the air. A simple Google search can yield these results fairly quickly, but it's important to make sure that these are in units of kilopascals to keep the units consistent. Lastly, we can plug in a value of 1 for the evaporation constant because it is simply a system of water and air. Putting it all together and solving for the flux, we get a value of 307.21 watts per meter squared. For the final time, we multiply this flux by only the surface area of the top of the pond to get the heat loss through evaporation as 30,721 watts or joules per second. Having done all of the initial hard work, we are finally able to answer the question initially asked by the problem statement. By taking the sum of all of the heat losses from all of the individual modes of heat transfer that we just calculated, we can get the total heat loss in the system. In this model, that gives us a value of 84,696 watts or joules per second. This is effectively equal to the amount of heat energy that needs to be initially input into the system to maintain the necessary pond temperature. It is worth noting that the largest contributor to the heat loss in this problem is that from conduction. However, eventually, the ground on the other side of the concrete pond walls will reach a similar temperature to the pond water. This will in turn make the thermal gradient approach zero, and correspondingly the heat loss from conduction will become trivial altogether. This leaves evaporation as the largest contributor to heat loss in this system in the long run. Overall, though, this is a crucial calculation that must be done when considering the size and design of the direct use system meant to supply this heat. It then needs to be evaluated for its economic feasibility to determine whether or not a direct use system is actually appropriate or not. The case study I chose to examine was Canyon View High School, located in Cedar City, Utah. This school has a direct use heat pump system that supplies its yearly HVAC needs. A diagram of this system is shown on the right, consisting of 300 boreholes. Due to the massive size of the school and the fact that the school was originally built with this direct use system, the cost of this system could effectively be compared to a traditional HVAC unit sized to meet the school's needs. What was realized was that the direct use system was actually substantially cheaper than installing a conventional HVAC unit. This translated into an immediate payback period on the capital costs required to implement the system. In addition to these savings, there was the added energy savings of $58,300 per year. While this case is a bit of a unique situation, with it being such a massive system and originally designed into the building, it still shows just how beneficial this technology can be. With a payback period of 0, lower CO2 emissions, and annual savings on energy costs, it is hard to find a downside to having installed this system. Direct use is becoming more and more common throughout the world. Where applicable, it can result in substantial energy cost savings. In some areas, there is even government incentive to invest in this green technology, as briefly mentioned in the video. This added to direct use systems having comparable pricing to traditional heating units gives direct use a substantial edge. Over the last 20 years, the amount of energy supplied by direct use has been increasing steadily, and as the need for clean, renewable energy increases, it can only be expected to increase even more. In summary, direct use geothermal is essentially governed by heat transfer. While it is what makes these systems physically possible, it also can sometimes hinder them and make them impractical. Direct use can be utilized in a ton of different applications and can frequently be both affordable and efficient. As drilling and the technology behind these systems evolve and improve, direct use will become even more economical and efficient, allowing for their spread into even more uses and geographical locations. As our society pushes to be more sustainable and environmentally friendly, this technology will only be further incentivized. This all translates into direct use geothermal being both a well-demanded and rewarding industry to get into right now. The quiz corresponding to this video can be found on the Canvas page under Direct Use. Thank you all for watching and have a nice day.